What's up, everybody? It's Miss Brothers. Hey, we're back, and we are with thermal energy practice number 1. If you watched the previous video, then you know that we went through and we did this first page. Now, this first page, just reminding you that this is the last practice that we're doing before we take the test on phase change and energy. And if you remember, we finished this last set of problems with problems 4 and 5, where we had silver spoon versus aluminum spoon. All right, the silver spoon and the aluminum spoon have the same mass. We heated them up the same, so they had the same change in temperature. The difference is their substance, silver versus aluminum, which means they have different specific heats. The specific heat of silver is 0.235, and the specific heat of aluminum is 0.897. And that's relevant when we start looking at the second page, because the second page starts right off talking about the spoons from questions 4 and 5. So question 6 says, which spoon from questions 4 and 5 required more thermal energy to heat to 75 degrees? Explain why it took more energy. Well, if I look at my answers, what I notice is that my silver spoon took 415 joules, give or take, where my aluminum spoon took 1,584.5 joules of energy in order to heat it up. So if we go back to our question saying which one took more energy, the aluminum spoon took more energy. And as far as the why it took more energy, well, it has a higher specific heat. Which means, in the case of aluminum, if we look at the specific heat of aluminum, we see it's 0.897. And so what that means, it means that it takes 0.897 joules of energy to heat aluminum. Well, I should say 1 gram of aluminum 1 degrees Celsius. It only takes silver 0.235 joules of energy to do the same thing. So just by the nature of aluminum being aluminum, it just takes more energy than it does silver. Silver wants to heat up faster. Aluminum doesn't. So aluminum is more resistant to that temperature change, to that heating, than silver is. So that's why. All right, so let's take a look at a little bit different situation. On the first page, what we dealt with is we dealt with everything Q's where we were putting energy into a system. So now what we're going to do on this next problem is we're going to talk about what happens when we're taking energy out of the system. So it says, what is the change in thermal energy of lead when 230 grams of it is cooled? And notice how the word underline is cooled from 90.8 degrees Celsius to 12.1 degrees Celsius. Now, this might kind of throw you off, and I noticed that as my students were working on these problems the other day, they were getting freaked out by the word cooled. Well, don't get freaked out, because we're still going to continue to go through the process. So instead of panicking about the word cooled, we're going to use our process, and then it's going to work itself out. Because remember, you guys, by following our process, process fights panic. Okay? So if we go back to our process, we're still trying to figure out what it is we're trying to find. And what we're trying to find is what is the change in thermal energy. And if we go back and we remember that thermal energy is Q, and if we use our triangle, we know that Q, if we cover it up, mass times change in temperature times specific heat. So that does not change. All of that stays the same, and we'll deal with the language of this question in a little bit. So Q equals mass times change in temperature times specific heat. Now let's go through the process and figure out what we know. We know our mass. It's 230 grams. Do we know our specific heat? We do, because we're dealing with lead, and if we look here, it says lead is 0.129 joules grams degrees Celsius. So we do know that. Do we know our change in temperature? Not quite, but we'll get there. So let's find that change in temperature. And remember, you guys, the formula for change in temperature is TF minus TI. Now, getting these two numbers right, which is the TF, which is the TI, is really a big deal, and we're going to see why it's such a big deal in this problem. So T equals, now again, let's go back to the language of what we have. Cools from 90.8 degrees Celsius. So it starts here. So that's going to be my TI. And then it cools to 12.1 degrees Celsius. So we know this is going to be my TF because it cooled down and finally got to 12.1 degrees Celsius. So now my T1 is 12.1 degrees Celsius minus, that's not a very good decimal, sorry, minus my TI, which is 90.8 degrees Celsius. So what a lot of my students want to do is that they want to say to themselves, well, 90.8 is bigger, so I better do my subtraction starting with that. But the truth is, you guys, you need to follow this formula from left to right, just like you would any math formula. So in this case, what you're going to be doing is you're going to be taking 12.1 minus 90.8, and that equals 78.7. Let me make sure I did my math right on that. 12.1 minus 90.8. Yep. So the number I get equals negative 78.7 degrees Celsius. Now this seems to weird out a lot of my students. They're like, how can I have a negative number? Well, you guys, the negative signifies the fact that you cooled. So if you see the word cooled in your equation or in a problem like this, what you need to remember is cooled means that if I'm trying to calculate change in temperature, my change in temperature is going to be negative. That's a big deal. The good news now is that we have enough information to fill in our Q problem, so let's do that. So Q equals my mass, which is 230 grams, times my change in temperature, which is negative, make sure you get that negative sign in there, 78.7 degrees Celsius, times the specific heat. And remember, we're dealing with lead in this problem, so my specific heat is 0.129. And let's go ahead and get that into my problem. 0.129 joules over grams degrees Celsius. So now, when I crunch my numbers, and let's go ahead and get those crunched, 230 times negative 78.7 degrees Celsius times 0.129 equals a negative Q number of 2,335 joules. And what that means is that we lost 2,335 joules as this lead cooled from 90.8 degrees to 12.1 degrees. And I just want to check my math on that. 230 times 78.7, and that is a negative times 0.129. Yep, that's what I got again. I'm going with it. All right. If I got this wrong, I know you will let me know. All right. Okay. So again, you guys, look, we're doing pretty much the same thing. What is the change of thermal energy? 230 grams lead, if it is cooled from 90.8 degrees Celsius to 65.7 degrees Celsius. So again, you guys, we're dealing with a lot of the same numbers again. This time we're dealing with lead again. We're also dealing with 230 grams, but this time our cooling, our delta T is going to be a little bit different because we're going from, instead of going from 90 to 12, we're going from 90.8 to 65.7. And again, looking for the word cooled, so we can expect our delta T or our change in temperature to be a negative number. So again, we're trying to find what is the thermal energy, or the change in thermal energy. So again, we're trying to find Q equals mass times change in temperature times our specific heat. And we're going to take a second because we know mass, we know specific heat, so now we're just trying to find that change in temperature. We started at 90.8, we finished at 65.7, and again, if we look at the top here, it says TF minus TI. So our TF is 65.7 degrees Celsius, and our TI was, oops, I'm going to make that a minus, sorry, that's not supposed to be multiplication. 90.8 degrees Celsius. So my change in temperature, if I take 65.7 minus 90.8. That means I have a change in temperature of negative 25.1 degrees Celsius. So now, your answer is going to be a little bit different. So we have a Q of 230 grams times negative 25.1 degrees Celsius, which shows me that this is cooled, times my specific heat, and if you recall from our previous problem, it is 0.129 joules over grams degrees Celsius, because I'm still dealing with the substance of lead. So my Q equals 230 times a negative 25.1 times 0.129 equals negative 744.7 joules. And again, as far as getting the unit of joules, it's because I've canceled out grams, I've canceled out degrees Celsius, and what's left is joules. And of course, I know that the unit for Q, or thermal energy, is joules, or J. All right, good. Let's go on to question number 9. It says, and again, you guys, please notice that if we are changing the temperature less, we lose less energy. If we change the temperature more, we lose more energy. See? Awesome. All right, let's go to question 9. It says an iron cube, ooh, that's probably important, with a mass, ooh, that's probably important, is placed into a stainless steel pot filled with boiling water for 5 minutes. The cube was 24.1 prior to being placed in the water, so that's going to be its initial temperature. At the end of 5 minutes, the iron cube is removed and has a temperature of 45.6. All right, so I know that's the last or final temperature, so that's going to be my TF. I'm going to make a note of that. How much heat energy did the iron cube gain? Well, that's what we're trying to figure out. How much energy? So if it's how much energy, guess what it is again, you guys? That's right. It's Q, and Q equals mass times the change in temperature times the specific heat. I sound like a broken record. But the more you practice for this, the more you just know what that formula is going to be. So again, you guys, we have to figure out that change in temperature, which is TF minus TI. And we determined, as we were reading the problem, that our TF is 45.6 degrees, and our TI is 24.1 degrees Celsius. So this tells me that this is going to be a positive number. So guess what? Our cube gained energy. So let's go ahead and do the math on that. And we're taking 45.6 minus 24.1. That's right. It's 21.5 degrees Celsius. So now we have enough information where we can complete our equation. We know everything we need. Our mass is 163.85 grams. Our change in temperature is 21.5 degrees Celsius. And our specific heat is going to be iron, so we have to go back to our chart, look for iron. There it is, iron. Our specific heat is 0.449, so let's go ahead and write that in. 0.449 joules over grams degrees Celsius. I know that's the unit for specific heat. Now I have enough to do math. Let's do math. 163.85 grams times 21.5 degrees Celsius times 0.449 gives me a Q of 1,581.7 joules. And I'm going to double check my math on that because I like to, how's that old saying go? Measure twice, cut once. 163.85 times 21.5 times 0.449. Yep, that's my answer. Okay, good. Now, it says let's go to question 10. Question 10 says, where did the thermal energy gained by the iron cube in question 9 come from? Give reasoning for your answer. Well, one of the things you have to remember about energy transfer, and this is any energy transfer. In this case, you guys, I can draw me a picture. Ooh, look, here's a picture. And look, this is an amazing pot of boiling water. I am an amazing artist. Here's the water. It's boiling. Yay. And here is my iron cube in the water. Okay. So this iron cube, the temperature of this iron cube increases, and it's not magic. It's just chemistry. All right? And what happens is that we know that in order for this this to heat up, what's heating it up? Yes, you have the burner that's heating up the pot. The pot heats up the water, and then what heats up the cube? That's right, the water does. A better way to say that is the energy is gained from the surrounding environment. And what we know for sure based on our question is that the surrounding environment is the water. Sorry, I'm writing really fast and really sloppily. The surrounding environment is the water. So if the iron gained 1,581 joules of energy, it means that the water lost exactly that amount. The way energy works, you guys, energy transfer, energy doesn't just disappear. It's got to be transferred. Okay? If something loses energy, that means something is gaining the energy. So this iron gained 1,581.7 joules of energy. It means that's what the water lost. So it's not brain surgery in this respect. It's just the fact that energy is not lost or it's not lost or gained is not the right word. It's not created or destroyed. It's just transferred. So in this case, iron's gain is water's loss, or water's loss is iron's gain. Kind of like how money works, and when you put it into one account or the other. You know, if you have a checking account and a savings account, and you take $1,000 from your checking account into your savings account, you still have $1,000. You just put it into different accounts. Same thing with energy. The iron is one account, and the surrounding water is another account. So if you take money or energy from the water and put it into your iron account, it's the same thing. You still have the money. It's just in different accounts. All right, I think I've talked about that enough. All right, guys, if you have any questions on this last sheet, just let me know. So far, so good. All right, if you have any questions, thanks.